Let's take a look at the idea of prime factorization. A prime number is a whole number that is greater than 1 and can only be divided by itself and 1. So every number can be divided by itself and 1. Prime numbers are special because they can only be divided by those factors. Some examples of prime numbers, if we just start with the smallest possible, 1 isn't included as a prime number, but 2 can't be divided by any smaller whole number. So 2 is prime. 3 is prime because we can't divide it by 2. 4 is not prime because 4 is equal to 2 times 2. So 2 divides evenly into 4. But 5 can't be divided by any smaller prime number, and so it can't be divided by anything other than 1 in itself. 6, of course, is 3 times 2, so that's not prime. 7 is prime, 11, and 13. And the list continues infinitely long. There's no limit to the number of prime numbers we can find. 2 is kind of special because it's the only even prime number. Every other even number is divisible by 2. If I have a number that's not prime, then it has to have a prime factor. 15, for example, it's divisible by 3, and 3 goes into 15 5 times. 3 times 5 equals 15. 3 and 5 are both prime, and so we call 3 times 5, we call that the prime factorization of 15. Prime factorizations are special because there's really only one prime factorization for any given number. Of course, 5 times 3 would be another way to write that, but it would be the same prime numbers. So prime factorizations are unique as long as we ignore the order of the factors. So let's look at a couple other examples. 12, 49, 30, and 42. So if I want to create factorizations of these, I can use what's called a factor tree. 12 is equal to 2 times 6. I can find just some factor pair of 12, and then think about whether those are prime. So 2, of course, we know is prime, but 6 can be split up as 2 times 3. So the prime factorization for 12 would be 2 times 2 times 3. 49 is 7 times 7. Both of those are prime, so the prime factorization would just be 7 times 7. 30 is equal to 5 times 6. Again, 6 is not prime, so I could write that as 2 times 3. Or for 30, if I thought of that a different way, 30 is equal to 3 times 10, but 10 is not prime. It's equal to 2 times 5. Both of those factor trees lead to the prime factorization of 2 times 3 times 5. Right, so no matter how we kind of split it into pieces, we should end up with the same set of prime factors. So both of those have a 2, a 3, and a 5. A 2, a 3, and a 5 as the prime factors. Finally, 42 is equal to 3 times 14. Of course, 14 is 2 times 7. If you thought of 42 as 6 times 7, then we would still end up with the same factorization, 2 times 3 times 7. We can think of prime factorizations as kind of the multiplicative building blocks of a number, and so if I'm interested in finding something like the greatest common factor, I can use prime factorizations to figure out what that would be. Because if two numbers have a common factor, then they would have to have a common prime factor. So I can see from the factorizations of 12 and 49 that they don't have any common prime factors, so they don't have any common factors. Whereas 12 and 30, they both share 1, 2 and 1, 3, and so the greatest common factor of 12 and 30 would be 6. So when we're working with numbers and looking for prime factors, maybe in order to find a greatest common factor, the most important numbers, at least if we're working with numbers that are less than 120, for numbers less than 120, the number is either prime or has 2, 3, 5, or 7 as a factor. So 2, 3, 5, and 7, if I'm interested in checking to see whether a number has a factor or can be factored in any way, if that number is relatively small, less than 120, those are the only numbers that I need to worry about, and then the other factors will kind of follow from that.